Greeting, ladies and gentlemen. Today we're going to fourth question. The allowable shearing stress is 100 megapascal in the 36 millimeter diameter steel rod AB and 16 megapascal in 14 millimeter diameter rod BC. So neglect the effect of stress concentration, determine the largest torque that can be applied. So essentially, I have a solid cylinder in the problem, AB and BC. For the AB, I have a allowable shearing stress 100 megapascal. For AB and BC, there will be 16 megapascal. What does it mean by allowable shearing stress? It is mean if you apply a torque and the torque produce a shearing stress as it then 100 megapascal, for shaft AB, this object will be failed. The same goes to cross section BC. You have a 16 megapascal, but if you exert addition torque, which is the torque then produce shearing stress as this value, then this shaft right here will fail. So our mission is to find the value of torque and match it with shearing stress that will be produced and not exceed the allowable shearing stress for both AB and BC. So that is the mission right there. So go through to the problem solving. As usual, you need to have a FBD for the entire system. Cut your FBD, your object from the support, which is what I'm doing here. So you will have a 3 point A, B, and C. You will have one torque, since that is been stated in the question, only one torque exert at point A. So there you kind of have it, which is the torque right there. But since that we were using this equation, which is, we call it as an elastic torsion formula, the value of torque in here, it is must respect to internal. So that's why you will have a different direction of torque, which is applied downward. If you take a look in the front view, which is in this direction, then you make this object horizontal and take a front view. Thus, the internal torque will exert downward. So you will have an internal torque, you will have the CBC, which is made two different analyses. For the first one, it is AB at point AB, and for the second one, there will be point BC. For the point BC, let's go through to point BC first. You will have an internal torque prime that you don't know the value is. You have an CBC that is referred to the radius for shaft BC. You will have an polar moment of inertia for BC, which is you simplify this equation even more. You simplify this equation even more, then you will get this equation. You include the value of C, which is 0.02 meter, come from the diameter of rod BC, which is 40. You divide by 2 and you convert it into meter, because the value of shearing stress that we were dealing, it is in megapascal. It is mean every single length that you are involved in must be in the unit of SI. For example, 14 millimeter, you need to convert into meter and cut it by 2, and cut it by half, thus you will get 0.02 meter, 0.002 meter, and same goes into this value. So there you kind of have it, 0.02 meter right there for the value of C in the form of meter. You include the value in the equation, thus you will get 754 Newton meter, 754 Newton meter for the first problem, and for the first cross section, which is CB. And for the second value of torque, which is at point A, B, you do same exact thing. You will have an allowable shearing stress different than BC, which is 100 megapascal, from the question, which is 100 megapascal in the 36 millimeter diameter steel rod AB. So you will have 100 megapascal. You will have an internal torque that you don't know. You will have the value of C, which is in the form of meter, 0.018. You get it from diameter. Then you will have a J, which is pi over by 2 C to the power of 4 in this state. I'm not simplify the equation. So you will have 0.018 in the upper side. Then you will have 0.018 to the power of 4 in the lower side. Thus, you calculate and get this value. But for the final value of torque, you need to take this one. It is because, imagine if you have 916.09 torque being applied at point A, according or respect to this equation, for point BC, you will have this torque value, and you will have a value of C for BC that will be 0.02 meter. Then, as this value will increase, the value of shear stress being produced at shaft BC will increase, which will exceed the allowable shearing stress, which will cause it to failure. So that's why the answer that will be 754. It is being said determine the largest torque, but why we didn't take this equation, this value? If we think logically, this value is more bigger than this one. Then I had give you the reason, which is if you take this value instead of this value, you insert into the first equation for the tau BC, then it will get the shearing stress exceed the allowable shearing stress, then this part will be failed. So that's why we take 754 Newton meter. It is the most largest torque that can be applied into a system, into the system right here, and avoid it from failure. So 754 Newton meter is the most safe, largest torque that can be applied on the system before and can avoid this system from failure. So I think that's all for today. Thank you for watching and have a nice day. Bye bye.